Hello everyone, today I'll present our work titled Exposing Functional Fusion, a new class of strategic backdooring dynamic prompt architectures. Let me start with a brief introduction. PFT is now widely adopted to adapt VITs to various downstream tasks. However, in this work, we identify a critical vulnerability in one specific branch of PEFT, dynamic prompting mechanisms. To demonstrate this vulnerability, we propose Viper, a backdoor attack that achieves superior clean accuracy and attack resilience through a completely new mechanism we call functional fusion. Every attacker wants to achieve three goals simultaneously. First, accuracy preservation. The points in the model must perform well on clean data to avoid suspicion. Second, computational efficiency. The attack module must have a small footprint and low latency. And third, attack resilience. The backdoor must survive common defenses like pruning. However, we found that the static PEFT methods, including LoRa and the standard BPT, cannot satisfy all three goals at the same time. This is always a trade-off. To solve this trilemma, we propose Viper. Viper introduces a visual prompt generator, or VPG, which acts as a dynamic conditional router. The VPG observes the module intermediate features and generates prompts on the fly. For clean inputs, the VPG generates benign accuracy boosting prompts, but for triggered back inputs, it injects malicious prompts that hijack the module prediction to a target label. This dual behavior is the foundation of our attack. We found that after training, the optimizer naturally consolidates both the benign utility and the malicious backdoor logic into the same sparse parameter core. Remarkably, this core contains only 0.27% of the total parameter. We conducted a dissection experiment. When we keep only this 0.27% core, the model still achieves over 90% clean accuracy and 100% ASR. But when we remove the core and keep only the periphery, the attack success rate drops to only 1.52%, and the clean accuracy falls back to the baseline level. This proves that the benign and malicious functions are not separate. As shown in this table, Viper achieves the highest clean accuracy across all 6 benchmark datasets. At the same time, it achieves near 100% ASR on most datasets. Viper consistently outperforms all baselines. Now, let me show you how resilient the Viper is against defenses. First, pruning defense. As you can see in the figure, Viper maintains 100% ASR even after pruning 90% of the module parameters. In contrast, the LoRa-based attack collapses completely after 16% pruning. Second, the neural cleanse, a popular trigger reversal defense. The neural cleanse fails to identify the true target class. The trigger it recovers achieves only 14.53% attack success rate, which is barely functional. Third, TSNE visualization. The poisoned features from Viper seamlessly merged into the target class manifold. This makes anomaly-based detection extremely difficult. Despite its power, Viper remains highly efficient. It only introduces 2.3 million trainable parameters. In terms of inference latency, Viper adds only 0.06 milli seconds of overhead. Moreover, Viper shows excellent cross dataset transferability. When trained only on ImageNet 100, it achieves over 99% attack success rate on 5 completely unsealed datasets. We also conducted ablation studies. As shown here, it detected robust to different prompt lengths, and with a trigger magnitude epsilon of just 0.5, both accuracy and ASR stabilize. To conclude, Viper exposes a new class of strategic backdoor in dynamic prompt architectures of VITs. Our core discovery, functional fusion, forces the benign utility and malicious logic into the same sparse parameter core of only 0.27%. This creates a hostage dilemma. Defenders cannot remove the backdoor without destroying the model's utility. Viper successfully resolves the text dilemma, achieving SOTA accuracy, near zero latency overhead, and a strong resilience against all major defenses. We urge the community to move beyond the static defenses to develop dynamic defense paradigms, such as inference time feature denosing or dynamic routing inspection. Thank you for your attention.